Hello, welcome to EC22 Lab. Today I'm going to be presenting Lab 1 Blinky. Blinky is a very simple program. Main goal of the lab is to write a program that flickers an LED at 1 Hertz. So the LED is going to be on for 500 milliseconds and then off for another 500 milliseconds. To achieve this goal, you will have to program a basic software delay using instructions that will loop around to just to consume time so that you can turn on and off the LED in the desired pattern. You are going to be learning a few basic instructions, particularly move T, str, LDR, B, sub, add, TST, TEQ. I'm going to walk you through some of them, but not all. The instructions I'm not going to talk about. You have to look them up in the reference and find how they work and how you can use them. The lab manual also has some examples using TST, TEQ, I think. You're also going to combine arithmetic and logic instructions with conditional branches. This is a very important part of the lab because it's what it will allow you to achieve your goal of writing this basic program that implements a software delay, and depending on how you approach the solution for the version B of the program, you will also use this to implement a structure that is similar to an if-then else. You have a video where I explain how to translate an if-then else written in C into assembly, so you can use that as a template to implement your program. So let's go and see what the Blinky template will look like when you see it in assembly. Well, this could be kind of the equivalent in C. So we're going to have a main function. I'm going to show you what the main looks like in assembly. Then the template comes with initialization code to initialize the GPIO-A, which is the GPIO to which the LED is connected. And the application also comes with a while loop. And your application code will go inside this while loop. And the reason why you have to do this is because, as I mentioned in Lab 0, the processor executes instructions sequentially. So imagine that you have the main function and you reach this point where you have the last instruction of the program. Assume there is some instruction to be executed here, even if you don't see it in C, might be present in assembly, and your CPU keeps loading instructions below this point. What's going to happen is that there is no guarantee that whatever is fetched from these addresses that are below the main are going to be valid instructions. And what will usually happen, and it will happen, is that the CPU will fetch a non-valid instruction code, and because this will throw an exception, you are going to end up in that exception handler I mentioned in the previous lab. So Blinky in pseudocode version A. There are two versions for this program. For more details, please refer to the manual. But basically the program will go something like this. You're going to write code inside the while loop, and I'm going to show you how it looks in assembly. But the idea is you can place your delay of 500 milliseconds, then you're going to turn the LED on, then you're going to apply another delay and turn the LED off. This is equivalent to what you have in that picture with the two different implementations, but in a flowchart diagram. Whatever method is better for you, you follow that. So I like the idea of having my implementation being written in pseudocode, like in this case, and then I can follow and try to translate this into assembly code rather than using the flowchart method. But that depends on your preferences and the way you feel much better. You feel it's better for you. Okay, so now let's move into version B. So before I show you the version B, the code for version B, think about this. We're using this delay here, and then we're using the delay again here. So this is a piece of code that will be duplicated, and we can try and save one of them by noticing that the turning LED on and turn LED off is pretty much the same thing. The only difference is that in one case, if the LED is on, I can turn it off. If the LED is off, then I will turn it on, or I can use some other mechanism to turn this LED on and off without even having to think about it, to implement a logic that will detect, that will find out whether it's on or off. So, but in general, the implementation will look something like this. Then we have the while loop, the delay of 500 milliseconds one time, and then we have if the LED is on, then you're going to turn it off, else you're going to turn it on. Now you can do this way, implementing it with the and if then else. So you read the LED status from the GPIO, and then you find out whether it's on and off, and then apply the appropriate action to it. But you can also use a bitwise logic function to perform this automatically. Keep in mind that if you take the route of using a bitwise logic operation to perform this, it will work in this case because we don't care about the other bits in the output port for the GPIO. But if you were to have more shared functions, particularly those that should not be affected by this action, then you cannot use that method. But it will work for lab 1. After lab 1, we should not keep using that, but it could save time. So this is what I have for the initial presentation of the lab. Now I'm going to go and show you the lab project, both in Proteus and in Microvision. The first thing I want to show you is the demo on how this should run. So if I run this simulation, which has the program already implemented, this is what you should be able to see. You should be able to see this LED turning on and off with an approximate 500 milliseconds period, with approximately one second period, which means it's 500 milliseconds off, 500 milliseconds on. I won't show you how to measure this right now because I have actual implemented code, and I don't want to show you that. But that's the main idea. Now, let me show you the project in Microvision. I'm going to close this demo because we're going to open the project in Proteus quite soon to show you some interesting features that you will see and may confuse you at first when you use Proteus and try to debug this code. So here we have lab 1 template. Remember, this is how we start our main function, and here we have the end of that main function. This code that you see here, all of it, is that initialization code that I was talking about. And we give you this because configuring the GPIOA is beyond the goals of this course, and you have to have some knowledge on how the peripherals work, what are the bits, and so on. So we're going to provide this for you for the majority of the labs. Just in lab 4, you're going to be involved with some of this type of code. Now, after this initialization section, we have that while loop that never stops. And this label here is where the loop starts, and this branch to loop just branches here. Because there is no code, when I build this project and I'm going to show you, this B is going to jump exactly to itself because there is no code in between this label and this instruction. But as you write your code, this target address that we put in the B in the branch instruction is going to change because now we are branching to some place and there are instructions in between that label and the branch instruction. Now let's go with a bit more of detail with the code. Now, let me zoom here so you can see much better. So what we have here are what we call defines in assembly, and this would be the equivalent in C to define, and then you define a macro. So the way you define a value in assembly is you have an identifier. So for example, let me use this one because it's easier to say and for you to understand. So this is the GPIO-A mode register, and so I write that because that is going to help me understand what's happening in the code. And then I write here the EQU keyword, and then I put the value I want it to take. And so what's going to happen during assembly time is that wherever the assembler finds this identifier is going to write there this number. And this is very good because it allows you to write self-documented code. Okay, the same goes for other defines that we have, and we use them all. These two in particular, I wrote them so you can use them as masks to turn on and off the LED using the best method, the safest method to do that. So now we move on to the configuration of the PIO. So here we have an example of using LDR. So LDR is load register. So we're reading this value into R1. So what is going to happen is that this value, which is this here, is going to be stored in program memory, in a section of memory that is read-only. And what happens is that when the CPU encounters this LDR R1, it's going to read the content of the address in which this item, in which this identifier was stored. And so RCC, B1E, and R is going to be an address, and in that address we're going to find this number 0x400-23830, and this is going to be stored here. Now then what we do here is we read with LDR into R0 the value that is located at that address that is R1. So in this case we're using another format for this instruction. So in brackets we need to specify an address, and that address is going to be this number here. So we're pretty much, what we're doing is reading the content of this memory location and putting that into R0. And then we perform an OR operation. So this is the OR instruction, it's a bitwise instruction, and we OR that to modify a bit on that register. And then we use the complementary instruction to LDR, which is STR, to write back R0 that now has this, the first bit is now 1 into the address to which R1 is pointing to. So you may have figured out that this construction here, it is what we call in C a pointer. So R1 is a pointer and it's pointing to this address, and I'm just writing this by loading that pointer address into R0. In this case I'm writing there. Now this is pretty much all we need to do to configure the PIO, including these lines of code here, where I'm just finalizing the configuration for the PIO. Once we reach this point, now we have PIO-A pin 5 configured such that we can write and read the LED. And this is what these instructions here do. This is an example of what you need to do in order to turn on the LED or turn it off. This is just an example, and you can use this in your program. You don't have to figure out a different way to do this. These 3 instructions in particular are what we would call a technique that is read, modify, and write back. And what that means is that because in most cases the registers, in this case we're talking about the DPIO data register, the registers in a peripheral are have bits for multiple functions. We don't want to, when we write onto those registers, we don't want to erase or modify any configuration or bit values that are there from previous configurations or previous actions that we performed on that register. Now, the way we save, we preserve whatever is there is by reading back into the CPU the value that is on that configuration or data register. Then we modify the bits that we want to modify, and we keep everything else the way it was before we loaded back. And then we write back. By doing this, we are using a safe mechanism that will not destroy any configuration or affect any other values that might be stored in that register on the peripheral. Now, this instruction here, TST, is doing nothing. It's just there to teach you, to give you a reference to an instruction that you can use for decision making. But in reality, there's nothing. So whenever you are trying to find instructions for logic expressions, you can come to this template and say, oh yeah, I know there is one there. Let me look for that one. This one is the same, but it's just performing the complementary operation of turning on off the LED. As you can see, again, we have the LDR, so we can read back the register value, and we modify, and then we write back onto the register file. So that's everything I had to say about the project in Microvision. Remember, when you create the project, you have to select the project and change in target 1 that the output is going to be in .elf format. That's all you need to do, and when you compile the project, it will create that .elf image file from which you can simulate. Let me now open the Proteus project. Let's wait just a few minutes, a few seconds until Proteus loads. Okay, there we go. Here it is. Now, remember, we need to load the program. It's l1.elf. And now I'm just going to run this. I need to show you the floating view. Now we have the floating view. And I want to bring in the registers so we can see the register file. And I'm going to put a breakpoint on this instruction and this instruction, because I want to show you something interesting that happens when we simulate this circuit. So now we're stopped at the instruction, and remember, I have in R0 a value set such that when I write that back into the peripheral register, the LED should turn on. So if I execute this instruction that is writing back to the PIO data register, you should expect this LED to turn on, but it's actually still off. And the reason why it's still off is because even though I've written back onto the peripheral register, that action happens at the end of the clock cycle, and therefore there's not yet enough time for this circuit to get properly polarized. What I mean by that is that the current has not started to flow yet because the simulation is stopped. But if I execute the next instruction, now you can see that it turned red here, and now there is current flowing and polarizing the LED and turning it green. So keep in mind that many times when this happens, you have to let another instruction execute so you can see that effect happening. So you have to account for the physics of the processes you are handling with, you're dealing with. The same will happen here. If I execute this instruction, the LED is not off, but when I execute the branch, it will eventually turn off. So some students ask me, what is a good way to start this program? And I say, okay, just copy paste these two pieces of code, you copy and paste them here. Let's get rid of the TST because we're not using this one right now. And let's try this. So if you remember before I copied and pasted this, actually let me show you. So we're here. And this instruction is branching. If I press F10, it will keep branching to itself. If I disassemble this, you will see that the PC target address is exactly the same branch instruction. That's why we're executing this unconditionally and forever. But if I stop the simulation, and now I build with this LDR and so on inside the loop, and I load my code again. So let me run. Let me clear all the breakpoints. If I run this, you may think, okay, the LED is not turning on and off, and you're wrong. The reason why you can't see it on and off is because it's happening so fast that there is no time for it to shine enough for you to see it. So the same effect that we use for movies, persistence of vision, is in this case working against you. But you can see that sometimes it's red, sometimes it's blue, because it's actually changing. Now let me put a pause here somewhere and let me disassemble this. So you can see that it actually turns and clear all the breakpoints. So if I put a breakpoint here, another breakpoint here, and I execute this step by step, now the LED is on, now it's off, now it's off, now it's on, and so on. Okay? So the other thing that I wanted to show you is that now branch has a different target address. So branch is now at 214, and if I disassemble it, it's now loading -18, which will be computed as a target address of 204, 1000 something 204, and this is the LDR instruction. So you see that this changed because I added code in between the label and the branch instruction. So that's it for the initial presentation. So what you have to do is to write your program with the loop inside this loop here. So it's going to be nested somehow. You can write the loop the way you want it. There is an example for if then else on a video. You can follow that as a template for if then else, but I don't recommend that you try to adapt that to become a loop, because if then else structures follow a sequence. So you have the logic expression at the beginning, and then you execute the then or the else block conditionally, of course. But for example, a for loop, even though it's going to have some similarities to an if then else, it goes back to check the conditional multiple times until it's no longer true and you break the loop. So that's how a for loop works. And so in that sense, it's different to an if then else, because in the if then else case, you check once in the for loop you check multiple times until it's no longer true. So, and that's going to change a little bit it's going to change significantly the template. So my recommendation is that you follow the idea that I exposed in the video, and then you try yourself to write your for template from scratch. And then once you have a template, just try it out with a simple logic expression and see if it works. If it works, then you have a working template that you can use for future videos. Now, in terms of the submission for this lab, what we're going to review both of them. So you need to submit a solution for the version A and then a solution for the version B on Learn. The date is already on your Learn schedule, so you have 15 days to complete this task and have it ready for us to check it out. That's it for the video today. Thank you for watching, and I hope you enjoy.